Like yesterday I was asking about the key points the day before. And so the key points the day before would be like endothermic, exothermic. But if you could get into more detail, like give me an example of an endothermic, give me an example of exothermic, And then if you were able to connect it to, let's say, the law of conservation of energy, like what we did with combustion of methane. And then if you were able to connect it to potential energy and kinetic energy, that's would be much better than just endothermic and exothermic. And so it depends on how detailed your notes are. Some people will just have endothermic, energies consumed, exothermic energies released. Other people will have a highly detailed set of notes where, they'll talk about a lot of different things. So this is why I just wanted to see, what people had in their notes to see, how detailed they are. And if they aren't so detailed, it's still just the end of the second week. At UCLA, they have professional note takers there. And the professional note takers, what they do is the professional note taker will have a meeting with the professors before they print out the notes to make sure that the note taker didn't miss any information, and that also to make sure all the information is correct. Well, we don't have a professional note taker, but in order to make sure that no information is missing, you can compare with other students, your friends in the class, or you can come and talk to me. I can take a look at the notes, and see if you're missing anything, important concepts or whatever, rather than these concept checks that we're doing now. The professional note takers will only do the lower level classes. They don't do the higher level classes. Higher level classes are small, and so we can't really afford professional note takers to come in there. And so you'd buy the notes. The notes aren't cheap, but everybody buys them. And anyway, so what did we talk about last time? What were some of the key things? Dimensional analysis. That's good. I'm sorry? Propagation of errors. Propagation of errors, what can you tell me about propagation of errors? What can you tell me about dimensional analysis, if there's like a take-home message about those? Like dimensional analysis, what did I say about dimensional analysis?
Use it to convert from
Yeah, we use it to convert from one unit to another unit, or one dimension to another dimension. Dimensions are just the units there. Did I say anything else about it? Almost all, like more than 90% of chemistry problems are solved using dimensional analysis. And so it's probably the go-to, but it isn't the only way, because can you solve temperature conversions or temperature relations using dimensional analysis? There we have to use an algebraic equation for that. And there are other techniques which we'll talk about that I'm going to add to this particular chapter. And so that's good, like more than 90%. So it's really important. What about propagation of errors? How many problems in Chem 4 are we going to do propagation of errors on? Practically all problems in Chem 4 are going to be solved using dimensional analysis. How many of those problems are we going to do propagation of errors? What is propagation of errors? I mean, because the thing is, even if I gave you a definition and wrote it on the board, you still want to rewrite the definition and put it in your own words. It's always good. It makes things easier to remember, but what did I say about propagation of errors? And what was the context? Well, propagation of errors, I was talking about that when we were talking about significant figures. The significant figures is a set of rules that we use to get some kind of estimate of the uncertainty or the error in particular numbers. That's what it is. But are those rules? What's the difference between a rule and a law? Yeah, there's usually exceptions to the rules. Sometimes you have to break the rules to get the correct answer. That's what you have to do with significant figures, because significant figures, you can't write a rule for everything, every possible scenario that comes up. And so significant figures, there are some known errors, some known problems with significant figures. If you want to, if you don't want to deal with that, because when you have rules, you always have to memorize the exceptions. You know, what are the exceptions? For example, in Chem 4, pretty soon we're going to have to memorize the solubility rules. And in the solubility rules, you'll learn that chlorides, bromides, and iodide salts are all soluble except for silver, lead, mercury. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. Those are the exceptions you memorize because the rules can't cover every single thing, and there's usually more exceptions to it. However, laws should be. And so it's not the law of significant figures, it's the significant figure rules, and therefore if we want a more rigorous way of dealing with errors in calculations, then we look at propagation of errors. But the problem with propagation of errors is that it's harder math. If calculus was a prerequisite for this class, then we would be doing propagation of errors instead. But calculus is not a prerequisite for this class, so we're just going to leave it at sig figs. Well, that's a compromise we make, And so that was the whole spiel about propagation of errors. How many problems are we going to do using propagation of errors in Chem 4? 0. We're going to do none, because instead we're going to use the rules for significant figures rather than what would be termed as a law, the propagation of errors. Or more appropriately, a law. It's not really termed a law, but you could think of it as a law. Okay. What else to talk about?
Precision and accuracy.
Precision and accuracy. Yeah. What's the difference? Give me an example of precision versus accuracy. Usually you want to define it in your own words. Yeah, accuracy, well, to have good accuracy, you have to eliminate user error and miscalibration, in order to have good accuracy. But it still might not lead to good accuracy, because accuracy is defined as how close you are to the true value. How close you are to the true value. And so being accurate means being correct. However, being precise doesn't necessarily mean being correct. Being precise just means that your measuring ability is very concise. That is, there's not much deviation, there's not much spread. And so, in other words, you're very consistent. If you're very consistent, then there's not much deviation between measurements. Let's say one measurement's here, one measurement's here, and so, or you're using higher precision instruments. If you're using higher precision instruments, it's easier to be concise. When you're using low precision, it's hard to be concise. For example, weighing this pen. If I weighed this pen just by feel, it's hard to be. Maybe I can just come up with some number, but it's hard to be concise, because you give this pen to one person and then you give it to another person. How close are they going to be as far as the measurements go? And so, but if you give this pen in a balance, so we're going to do balances today, then you can be more concise. So good. You want accuracy and precision, and how do those relate to significant figures? That's one thing we talked about yesterday, right? How does accuracy and precision relate to significant figures?
The more precise it is, the more significant figures, but that doesn't mean the more accurate it's
Yeah, that's exactly right. The more precise, the more sig figs, but it doesn't necessarily mean it's more accurate. That's the take-home message from that. Okay, anything else that we talked about? Conversions, right? Metric system. Certain versus uncertain digits. Good. Density. Temperature. Temperature scales.
Temperature scales have a linear relationship.
Temperature scales have a linear relationship. That linear relationship just means that there's no squared term or cubed term in there. That's it. There's no weird behavior, like. Okay, what else for temperature? Kelvin and Celsius use the same scale as in step size, you know? Yeah. So one Kelvin step is the same as a 1 degree C step. Whereas a Fahrenheit step would be bigger or smaller? Smaller, Fahrenheit step. So, but you know, how big the step is just depends on who defines the scale. You know? You can make very fine steps or very coarse steps. Anything else? Yeah, the temperature. An example. If somebody asks you an example of empirical equation, you could give them the equation for temperature because that's an empirical equation, which means what? It came from observation. And so the other thing that came out of this was this is the scientific method, but we took the scientific method only to the law that governs the relationship between Fahrenheit and Celsius. Are there any exceptions to that law? You know, if I convert it, do I have to remember exceptions? Like, oh, the Fahrenheit temperature is equal to this unless the Celsius temperature falls here, 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 and here. Would there be exceptions like that? No. So that would be considered the law of temperature. There's a chair here. Okay, I got to figure out what I'm going to do about the drawers here. Situation. But in a lab class, just for future reference, in a lab class, like at UCLA, if you miss the first lab, you're out, basically. You're out. And so in the lab classes I had. And so be careful because the lab is most important in a joint class like this, but be careful that your drawer doesn't get assigned, because I assigned the drawers already to other people, so I have to figure out how to fix it later today. So we have too many people now, but maybe we can squeeze some in. But that was all part of the scientific method. So this was just yet another example of the scientific method, but the scientific method wasn't taken all the way to theory. You know, we stopped, and that's often what happens. Many times when we do the scientific method, we don't have to go through all the steps. What were the steps of the scientific method? And this should be pretty easy because it was discussed on day 1, so there should be a lot of repetition by now. Observation, pattern, law, hypothesis, and then theory. Good. And so oftentimes we just stop at observation, you know, or looking at patterns. You know, it's not just physical scientists who do this. I was listening to a TED Talk. It was a social scientist, and what she said she does is she takes all these surveys or whatever forms and throws them all over her floor. And then she looks at all these surveys and then tries to see patterns arise from all the data. And then go from there, come up with some math that describes that particular pattern. And so sometimes we'll just go to patterns, and then just try to use the patterns to make predictions. And so this goes back to day one. In day one, is science all memorization? No. Is science all theory? There are two camps. There's a camp, and I already emphasized this point, but let me just mention it one more time. And that is, there's a camp of people who think memorization is bad. But when you think about it, observations, all those observations are essentially just like memorization, memorization of data. We write it down so we don't have to necessarily memorize it, but when you're looking at the data, the way to really understand the data, the way to really find the pattern is to have it like memorized, because when you have that data memorized, then you can better see patterns that might arise, or you just look at it as a whole. And so in science, there are two camps as well. So for example, that large collider in Switzerland, there's a pretty big collider. What was the name of that collider? The name of the collider is not that important, but it's a large Hadron Collider. And then there are two camps. If you watch the videos, they're the theoretical physicist versus the experimental physicist. And so the theoretical physicists predict one thing, the experimental physicists predict another thing. And the same thing happens in chemistry. So for example, I don't want to memorize water as a liquid. Why bother memorizing water as a liquid at room temperature when we can easily look it up, or we can find out that type of information? Or maybe, to really truly understand chemistry, you need to know the theory. And so what we should do is, instead of memorizing that water is a liquid at room temperature, we should be able to predict that water is a liquid at room temperature theoretically. So I haven't talked about the chemistry, the theory of chemistry. The theory of chemistry is, atomic theory, and then digging deeper into atomic theory, we have something called quantum mechanics. And so when we look at the theory of chemistry, it turns out that the math that's involved in the theory is so horrendously difficult that people have to guess. They guess their answers. The guessing their answers is very common in science because the math sometimes is too difficult to actually solve. And since that's the case, we don't call it a guess, though. We call it approximations. We do approximations in order, but approximations are essentially guesses. And so to prove that water is a liquid at room temperature, theoretically, without memorizing this, is a horrendously difficult calculation. You got to use it like a computer to do the calculation, essentially. And so to approach everything from a theoretical standpoint is quite a big challenge. But there are people who do this. There's always the case. If you go to a drug firm, there's the theoreticians, and then there are the experimental people. The theoreticians get on the computer and design a drug. This drug should be the perfect drug for that specific target. And so they design it on the computer. But when they do those calculations, are those calculations 100% accurate? Are they? No, because the math is too horrendous. So they have to make a lot of guesses when they do those calculations, and those calculations are approximations. So when they generate this structure, it's an approximation. This is the best structure that they predict. This is why they want supercomputers. They want supercomputers because with supercomputers, you can make fewer and fewer guesses. And the weaker the computer, the more guesses you have to make as far as how it works. But then it has to be verified by the experimental. And so, the theoretician will come up with this and then have the experimental chemist do this. And sometimes that target isn't, what they generate on the computer isn't the best. Sometimes what the experimental chemists will do is they'll make a whole bunch. They'll make a series of drugs, by changing, maybe the wrong term. By changing certain structural features or certain atoms or certain whatever, and they'll make a whole bunch of different potential candidates, and then find out experimentally which one's the best. Right? And so what we do is, this goes back to day one. What we do is the two-pronged approach to studying chemistry. What we do is, we don't want to approach it entirely theoretical. We don't want to memorize everything, because memorizing everything is a bit too much. And so what we want to do is, we want to do a hybrid approach in which we look for these patterns, patterns in structure, composition, and properties that we can use to make predictions. And so there is going to be quite a bit of memorization in this class. And I know that people have mixed feelings about memorization, but it's crucial, because memorizing water is a liquid is a heck of a lot easier than proving it theoretically. And when you prove it theoretically, people are going to challenge your proof, versus memorizing, it's a fact. Nobody's going to challenge that. Okay. All right, so that was an example of the scientific method. Was that it for review? All right. So that's pretty much it. So the next thing I wanted to talk about is the relationship between percentage, parts per million, parts per billion, and parts per trillion. And so we're going to do, because some of the dimensional analysis problems in our book are a little too easy. And what do I mean by too easy? What I mean by too easy is the next class. The next class is too hard. And so if Chem 4 is too easy and Chem 1A is too hard, then we got to come up with some kind of intermediate step, so that the step up isn't too big. And so let's take a look at number 69. So can you write down this problem here? And we'll work on solving that. I'll be right back. Did you guys get it? So number 69 says a solution used to chlorinate a home swimming pool contains 7% chlorine by mass. An ideal chlorine level for the pool is 1 part per million. Think of 1 ppm as being 1 gram of chlorine per million grams of water. If you assume densities of 1.10 grams per milliliter for the chlorine solution and 1.00 grams per milliliter for the swimming pool water, what volume of the chlorine solution in liters is required to produce a chlorine level of 1 ppm in an 18,000 gallon swimming pool? So this is a pretty challenging problem, and if you think about this particular problem, and we go back to chapter 2 or chapter 3 in our book, and so what we're doing is we talk about dimensional analysis in chapter 3 of Chem 4, and then this is chapter 1 of Chem 1A, and so right away it's like boom, you know, it's a pretty big jump in level of difficulty, because in chapter 3 of Chem 4, none of the problems get anywhere close to this difficult. But you know what? This isn't really that difficult, and it shouldn't be a big or terrible jump. The problem here, what makes this particular problem difficult, is that people don't label things with enough detail. And so the biggest mistake that people make on this problem, number 69, is that if they were just a little more careful in how they labeled the dimensions or the units, they probably could have solved it. I think, and so that's problem number 1. Problem number 2 is people don't know what ppm are, and so if this is your description of ppm, it throws people off. You know, ppm is not really discussed in chapter 1 of this book. It's they just tell you here, this is what a ppm is. And so the first thing I want to do is I want to just talk about percentages and ppm, and then the next thing I want to do is talk about labeling dimensions or labeling units, and then we should be able to solve this just using the techniques that we have. And so if we go back to the first sentence there, it's 7% chlorine. And so this is what we call a chlorinating solution. And so the chlorinating solution is 7% chlorine. Now, what is chlorine? Well, chlorine is one of those things that you memorize as being a... What's special about chlorine? It's a diatomic. Right. And so does that mean it's 7% Cl2 or 7% Cl? And so you would think Cl2, but did you know that Cl2 is normally a gas, liquid, or solid? Well, I don't want to memorize that. I'd rather just predict it or look it up. Well, it turns out that Cl2 is a gas. It's a green gas. That's normally. And if you add Cl2 to water, what we can get is something called chlorine water. But Cl2 is not very, what we say, soluble in water. And so we can't get all that much. And so there are other things that have similar action to Cl2. And the other things that have similar action to Cl2 would be like bleach. Bleach, you know chlorine bleach? When you buy chlorine bleach, are you buying Cl2 in water, or are you buying something else? Have you looked at the ingredients of bleach? When you look at the ingredients of bleach, it says sodium hypochlorite. A sodium hypochlorite is NaOCl. Well, NaOCl, is that chlorine? No. But what happens is, because of the chlorine contained in here, it has similar bleaching properties as chlorine. You know, chlorine will bleach your clothes quite as well. The same thing with sodium hypochlorite, NaOCl. And so this is bleach here. So there are other chlorinating compounds. There are other compounds, or, this is an element, but there are other species that have a bleaching action like chlorine does. And we'll talk about that bleaching action later when we get into chemistry. It's called an oxidizer. But anyway, here, so I don't know, because I don't know. It says it's used to chlorinate a home swimming pool, contains 7% chlorine by mass. It might be pure chlorine. If it's pure chlorine, then we're talking about Cl2, if we're talking about pure chlorine. But if it's chlorine contained in a compound, then I don't know what that compound is. And since it's not specified here, all we can say is it's got to have 7% chlorine atoms by mass. And so what does that mean, 7% chlorine atoms by mass? Well, it means this. A percentage, another way of saying percentage is it's a part per 100. And so percentage is a part per 100, which means that we're going to have 7 parts per 100 parts. And so we have to be more specific. Parts of what? And so this is where it gets into labeling the dimensions here, because in terms of labeling, this is going to be parts of chlorine, Cl, per 100 parts of chlorinating solution. Chlorinating solution. But the parts, we have to be more specific. What are the parts? Is it 7 gallons of chlorine for every 100 gallons of chlorinating solution? What are the parts? And so here it's by mass. And so we could pick any mass unit. And so the parts would be 7 pounds of chlorine per 100 pounds of chlorinating solution. That's fine. But do we use pounds much? What do chemists use mostly? Grams. Since chemists use grams mainly, we're going to stick with grams. So it'd be 7 grams of chlorine. This would also be pure chlorine, because it would just be atoms of chlorine. But those atoms of chlorine can be incorporated into compounds, but we're ignoring that. Out of a total of 100 grams of chlorinating solution. And so the other way to get around this is if we just label it 7 grams of, since I don't know, maybe it is Cl2. Maybe they're making just chlorine water. I don't know. And so you might just write 7 grams of chlorine over 100 grams of chlorinating solution. Does that make sense? There, right? This is just percentage. And so the problem is this. What if I don't want to write? I'm tired of writing, so I'll just write 7 grams out of 100 grams. Does that make sense? There. The worst is some people don't even bother writing grams. And so they use this for anything. They'll use it for gallons, they'll use it for they'll use it for anything. And then they get the wrong answer here because it doesn't work for anything. It just works for mass. And so this is, and then they'll use this and they'll get it all mixed up because it's 100 grams of what per 7 grams of what. And so here is the biggest error. The biggest error is just simply labeling this 7 grams of pure chlorine per 100 grams of chlorinating solution. Chlorinating solution is a mixture. And so how many grams of chlorine atoms am I going to find in this mixture? That's it, 100 grams of that mixture. All right, what if I had 1,000,000 grams of the mixture? How many grams of chlorine would I have if I had 1,000,000 grams of mixture? If I had 1,000,000 grams of mixture, then this is what I do. Rather than out of 100, I'm going to go with 1,000,000. So I need to move the decimal over. 1, 2, 3. It'd be 100,000. One more. This would be 1,000,000. Right? If I move the decimal over 1, 2, 3, 4 places, then I'd have to do the same thing here. 1, 2, 3, 4. And so 7 grams of chlorine per 100 grams of chlorinating solution is the same thing as 70,000. I'd have 70,000 grams of chlorine per million grams of chlorinating solution. And so this says the same thing. You know, if I had 1 gram of chlorinating solution, how many grams of chlorine would I have? Well, if I had 1 gram, I'd move this 2 decimal places this way to get 1 gram on the bottom, and then I'd move this 2 decimal places over this way, and I'd end up with 0.07 grams of chlorine per 1 gram of chlorinating solution. And so this is the same. Let's say I had 1 billion. If I had 1 billion, then I just need to add 3 more zeros. 1, 2, 3, add 3 more zeros here. So if I had 1 billion, it would be equal to 70 million grams of chlorine for every 1 billion grams of chlorinating solution. And so we come up with this. We come up with 7 grams per 100 grams. This is equal to 7%. If we have 70,000 grams per million grams, this is 70,000 ppm, parts per million. If we have 70 million per billion, this would be 70 million ppb. And so all these are the same. 7% is exactly the same thing as 70,000 parts per million, which is exactly the same thing as 70 million parts per billion. And so the relationship is, if you know how to deal with percentages, then you know how to already deal with parts per million and parts per billion. And so let's do just one more example here. And this one's not going to be by mass. This is going to be by atom. If we look at H2O, what fraction of H2O is hydrogen? Well, there are 2 hydrogen atoms for every 3 total atoms. And so what we're going to do is we're going to get percent by atom here. Not percent by mass, because the mass ratios are different. But if we do percent by atoms, what do we do? How do we convert a fraction into a percent? Do you know how to convert a fraction into percent? To convert a fraction into percent, we multiply it by 100%. So if we take this, it's 2/3 hydrogen. If we take that and multiply by 100%, we get that this is going to be 67, I'm rounding here, 67% hydrogen by atom. Not by mass. The hydrogen atoms don't weigh much compared to oxygen atoms. Oxygen atoms weigh like a lot more, 16 times more. And so we had 67% hydrogen by atom. Now, this is a part per 100. If we want to go to part per million, what do we do? To go to part per million, what we do is we take the fraction and we multiply it by, not 100%, we multiply it by 1,000,000 ppm. If we multiply by 1,000,000 ppm, then what does that come out to? That comes out to 670,000 ppm hydrogen. And the way we look at it, these two are the same, because what this says is parts per 100. So we have 67 H atoms for every 100 total atoms. There's round off error here, because I had to round it. Over here, this says the exact same thing, except rather than doing it out of 100 atoms, we're doing it out of a million. So this is going to say there's 670,000 H atoms for every million atoms total. And so we know how to convert from fraction to percent. We know how to convert from percent to fraction. We know how to convert from percent to decimal. Right? What would this be in decimal form? In decimal form, this is 0.67. Right? 0.67 out of 1. So 0.67 H atoms out of every 1 total. In other words, 0.67. In terms of decimal, this is the same. No? Not this. Yeah, it is the same. 0.67. Okay, and then to go to parts per billion, if we take our fraction, rather than multiplying by 100%, rather than multiplying by a million ppm, we're going to multiply by a billion. A billion ppb. And that'll convert it into a parts per billion. So this would be 670 million parts per billion hydrogen by atom. And so in other words, we can go back to fractional form, which would be like this: 670 million out of 1 billion total. All right, so we're going to be dealing with percentages on parts per million and parts per billion, and maybe parts per trillion. If we had a part per trillion, what would it be? Well, how would we get a parts per trillion? We'd multiply it by a trillion ppt. And so it follows all the same rules that you have for percentages. We manipulate them. It's just a matter of convenience, you know. Out of all, since all these say the same thing, which one's easiest to say? Percentage, parts per million, or parts per billion? Percentage, for sure percentage, because these are huge numbers. Those are huge numbers. But when we're dealing with very small compositions or very small fractions, let's go to 1 gram of chlorine here per million grams of chlorinating solution. If we want this in terms of percentage chlorine in the chlorinating solution by mass, what would it be? Well, we take our fraction and multiply by 100%. We take our fraction and multiply by 100%, we get what? So that's 10 squared, this is 10 to the 6. This would be 10 to the minus 4. And so it would be 0.0001% chlorine. And so 0.0001% chlorine is the same thing as 1 part per million. Or we'll try ppm chlorine. If we do ppm chlorine, then we'll just multiply it, rather than multiplying by 100%, we're going to multiply it by a million. If we multiply it by a million parts per million, then the grams cancel, the million cancels, and we're left with 1 ppm chlorine. Or if we want it in terms of parts per billion chlorine, and so the swimming pool contains, or should contain, 0.0001% chlorine, or it should contain 1 part per million chlorine, same thing. Or in terms of parts per billion, we'll multiply this by billion. If we multiply by billion ppb, then we're going to get, this is going to be 1,000 parts per billion fluorine. And so it's just a matter of convenience. Which one is the best unit to use? Percentage? Well, percentage is kind of a hassle because it's a small number. Parts per million? Parts per million is good. I mean, it's one, it's easy to say. Or parts per billion. Parts per billion, well, 1,000's too big. It's a hassle. And so we just pick the one that's most convenient. And that's what we do. We just see which one of these is most convenient and use that. And so for certain things, you know, a part per million is cumbersome. 670,000 parts per million, that's cumbersome. Why? Because it's kind of high. The concentration is kind of high. This is concentration or composition. If the composition is kind of big, then we want to use percentages. But if the composition is very small, then we'll probably not use percentages. We'd probably use parts per million or parts per billion or parts per trillion. It's a lot easier than dealing with very small numbers. All right, so does that make sense for that? Now, this is not in the book, but of course you can find it on Wikipedia or whatever else. But pretty much when you get to Chem 1A, they're just going to jump into it like this, and then we'll have to deal with it as it goes along. All right, then for number 69, we're going to come back to that next time. We'll look at how to solve this particular problem using a dimensional analysis approach. So that's another way. All right.